A rocket is falling out of the sky, and there are no landing legs beneath it. In seconds, a moving ship must catch it with wires. Hello and welcome to Qoxum. Today, we are rebuilding this extraordinary recovery step by step, using the real vessel and the reported engineering sequence. This is Linghangzhe, the recovery vessel. It is about 144 meters long, 50 meters wide, and displaces roughly 25,000 tons. The structure is not a solid tower. It is a huge open rectangular truss, fixed to the deck through 4 major supports. The empty center creates a capture corridor. The booster must enter from above while the ship, frame, sensors and cables operate around it. Across that opening is a controlled wire arrest system. Pretension cables form intersecting capture paths, supported by movable hardware around the frame. LiDAR units at the 4 corners measure the returning stage's position and attitude, giving the vessel a live picture of the closing geometry. Linghangzhe uses dynamic positioning. Its thrusters can correct the vessel's heading and location, so the target itself helps meet the descending rocket. After stage separation, the first stage starts a 6-minute journey back through the atmosphere. Recovery is already an active guidance problem. Attitude control thrusters rotate the stage, while 4 grid fins unfold near its upper section. Together, they steer the falling cylinder. Selected engines reignite for the first braking burn. The goal is not to hover, but to remove enough speed while preserving control authority. The engines shut down again. As the atmosphere thickens, aerodynamic drag dissipates more energy, and the grid fins keep trimming the trajectory. Lower down, a second burn further reduces the descent rate. The recovery vessel is now visible beneath the clouds and closing rapidly. This is cooperative guidance. The rocket corrects its path while the DP2 vessel adjusts its own position toward the same predicted capture line. As the booster approaches, the corner sensors refine its position and attitude. Small errors now matter because the capture hardware has limited travel. The arresting cables ride on rail-mounted sliders. These carriages reposition under tension, moving the effective capture zone toward the incoming stage. Coordinated cable motion gives the system more tolerance than a fixed target. It can respond to the rocket's final lateral and angular errors. During most of the flight, the 4 capture hooks stay compact and flush near the upper capture zone. The tank body remains clean and unobstructed. Only in the final seconds do those hooks swing outward. There are no giant boxes, rings, or ship cables strapped around the middle of the booster. The first stage descends directly into the open frame. A small final plume controls speed while the ship holds the target beneath it. The engine section enters the rectangular opening first. The frame remains clear on every side, leaving room for controlled movement and cable positioning. Just before engagement, the engines shut down. From this point, the arresting system must take the remaining load without a hard deck impact. The deployed hooks meet the tension cable paths near the upper capture zone. The stage stays vertical as the load transfers into the frame. Each compact hook engages a cable. The cable moves through its carriage and buffer system, instead of being tied directly around the rocket. The specialized cable system stretches and pays out under controlled resistance. That converts the remaining motion into managed mechanical load. Viewed from above, the cable paths distribute force around the centered booster. This is an engineered arresting system, not a fabric trampoline. After the capture, the stage hangs inside the open frame. Its engines remain above the deck, and the main cables support it near the top. Auxiliary stabilizing cables then deploy around the booster. Their job is to reduce residual movement, while the main arresting system carries the weight. An automatic clamping platform moves underneath the suspended engine section. This happens after the cable capture, not before the rocket arrives. The lower platform aligns with structural hardpoints, closes its padded clamps, and locks the stage into a stable transport configuration. Only now is the booster fully secured. Upper cables hold the captured stage, lower supports stabilize it, and the open frame contains the operation. Deleting landing legs can reduce hardware carried through the whole mission and widen design choices, but it transfers complexity to the ship and capture system. The recovered first stage carries 7 engines. Bringing that complete engine section home gives engineers valuable hardware for inspection and possible reuse. A successful catch does not automatically prove rapid reflight. Engineers must inspect structures, engines, thermal protection, plumbing, and the loads recorded during capture. The vessel can now return with the secured stage. The bigger question is how much refurbishment it needs before the same hardware can fly again. So the real system has 4 essential parts: a moving ship, an open frame, coordinated arresting cables, and hooks near the booster's upper capture zone. Thanks for watching.